Hello and welcome to lesson 2.2, characteristics of polynomial functions in factored form. So in order to recognize what we're going to see today, what we're going to do is we're going to take a look at a few functions, both their equations and their graphs. And their equations are going to actually be listed in factored form. So the first function I'm going to look at is f of x equals x plus 2 times x minus 4, as you can see right here. And we're going to notice what the zeros are, and then we're going to look at what the function is. So in order to find the zeros, what you do is you set the function itself to 0. And you get this expression. Well, what you can notice from this is only you have two options. You can either only have x plus 2 is equal to 0, or x minus 4 could equal 0, because this is a multiplication. So that's what I'm going to do. I'm going to write down x plus 2 equals 0, or x minus 4 equals 0. That's the only two options you have. Well, if you solve each one, you get this one as x equals negative 2, and you get this one as x equals 4. And what you can see on your graph, there's that point, x equals negative 2, and there's that point, x equals 4. Well, the other option of this is you realize that the leading coefficient right here is a positive 1, and that gives you your end behavior that you're seeing right here, so that it's going as x approaches positive infinity, y approaches infinity, and as x approaches negative infinity, y approaches infinity. Okay, so some other aspects you can figure out from this. You can also figure out your y-intercept by just substituting 0 in for x for your function, and seeing you get a value of negative 8. Okay, so let's take a look at the next type of function. So this is one of those cubic polynomials we were talking about earlier. And again, to find our zeros, we set this function equal to 0. We leave everything else as is. Well, our factors in this case are negative 2, x minus 1, x minus 3, and x plus 3. So any of these things could equal 0 except for one of them. The first one, negative 2, cannot equal 0. So you're only interested when x minus 1 equals 0, or x minus 3 equals 0, or when x plus 3 equals 0. So if we solve each one of these, I get x values of 1, 3, and negative 3. Which you can see right here, this is x equals negative 3, this is x equals 1, and x equals 3. The leading coefficient in this case is negative 2, and that gives us our end behavior that we see right here for this polynomial function. Okay, let's move along. Let's see something a little different. Well, this one, take a look at the function here. Well, we can set again h of x equal to 0, and then we can solve. Well, this means 3x could equal 0, or x plus 2 squared could equal 0. Well, if I divide both sides of these by 3, I get x equals 0 as an option here. If I square root both sides here, get rid of the squared. Square root of 0 is just 0. Square root of x plus 2 squared is x plus 2. And solve this, you get x equals negative 2. So here you see you have two zeros. And you can see them right here. You have your x equals 0, and you have your other shape of x, other 0 at x equals negative 2. Well, you'll notice the shape for this x equals negative 2 is a little different. So this 0 has a different shape. It looks like it kind of like just bounces off the x-axis there. Well, that bounce comes from this exponent being 2. When you have your exponent being 2, it kind of gives it like a quadratic shape. So it kind of like just sits on the axis at that point in time. And that's what's going to happen when you have an exponent of 2. So, what might be your next logical question is, what happens when you have an exponent of 3? And that's where we're going to go with this one. So we can set this function equal to 0. We can solve each piece. So we can either have 12x cubed equals 0, or x minus 2 could equal 0. On our second expression, either x could equal 0, or if I divide both sides by 12 here, let's divide both sides by 12. I get x cubed equals 0. I can cube root both sides. It just gives me x equals 0. So you see, you get zeros at x equals 0 and x equals 2. Leading coefficient is positive, so that's what gives you your end behavior. But if you look at the shape right here, as it goes through the x-axis, you'll notice it's got this cubic shape, kind of like the base cubic function, which hopefully you guys were introduced to or you saw in grade 11 university. If not, that's what a cubic function looks like. It goes right through the x-axis and kind of like hovers there, or has a little valley or whatever you can say. It just hovers at that spot as a slow decrease at that spot and slow increase, or vice versa. Okay? So, polynomial functions can be written in this form, in factored form, having a leading coefficient, and could be multiples of x minus b to the n, x minus b to the 1, x minus b to the 0, x minus b to whatever base value you have. So that a polynomial function can be written in factored form. That's one of the ways that you can write a polynomial function. We also saw it can be written in standard form in our first section. Please realize the numbers a and b subscript whatever value you have is a real number, and all your subscripts are natural numbers. In other words, numbers like 1, 2, 3, 4, 5, 6, so forth. Now, to determine the equation of this function in this form, you are required to know your zeros and at least one other point on the curve. If you don't have this information, you're not going to be able to figure out all this information. Okay, so let's take a look. So here I have this function drawn here. I can see I have zeros at x equal to -3, at x equals 2, and at x equals 5. These are my zeros. Okay, now I'm going to start writing down this function. I'm going to call it f of x. But the thing is, I don't know what the stretch or compression factor is, and I don't know what the leading coefficient might be. So I'm going to put a value of a, just an unknown value. But my factors, because one of my zeros is x minus 3, the first factor should be x plus 3. The second factor because the 0 is x equals 2, the second factor should be x minus 2, but notice how it has that quadratic-y feel right there. It just bounces off the function, and bounces off the x-axis. So that means it has an exponent of 2. And my other factor, because of my 0 is x equal to 5, should be x minus 5. Now you can notice I have one other point listed right here. It's point -1 and -4.5. So what we're going to do is we're going to substitute that into our function. So if x is equal to -1, f of x is -4.5. Like so. Okay, so now I'm going to work this out and solve for my value for a. And if I can find my value for a, then I got this expression. So this is going to be 2, -3 squared is 9, -1 minus 5 is -6. I'm going to grab my calculator right now and multiply these values out. So this is -4.5, and this is going to be -108. So a is going to be 4.5 over 108. Not a good way to write a fraction, so I'm going to write it as 45 over 1080 first. And then I'm going to try to reduce this fraction. Using my calculator, I notice a is equal to 1 over 24. So therefore, this function, as you can see, it has a positive leading coefficient, so it must be a positive value. Must be this function right here. So, as we can see, we've got this kind of function right here. Now another way of expressing some of these zeros, instead of it being quadratic or cubic or linear, sometimes they call these order 1. This one has an order of 2, because of the exponent being 2, and this one they call order 3. So you can use those terms as well. Okay, so let's go back to our examples. So we want to determine a function, f of x, with zeros of 2, of -3 at order 2, so that one's different, and 1, and goes through the point 3 and 12. So again, I'm going to write f of x. I don't know what my stretch or compression factor is, but I have zeros of x equals 2, so it's going to be x minus 2. 0 at -3, so that's going to be x plus 3. But that's going to be order 2, so I'm going to have an exponent of 2 on that. And a 0, 1, so x minus 1 is my other one. So now I've got that. I substitute my point in, so f of x is equal to 12 when x is equal to 3. So I substitute 3 in. And now it's just a matter of solving. So 3 plus 3 is 6, squared is 36, this is 2, 36 times 2 is 72, I know that one, times 1, okay, so a is going to be 12 over 72. Well, this expression I do know, 12 goes into 72 6 times, so this should be 1 over 6. There's my function. And there we go. So not only can we use the zeros and a point to figure out the equation. But we can also use the equation or the expression that we have here in factored form to give us an idea of what the sketch of the function may look like. So that's our last example that we have right here. Okay, so here, based on this function, f of x equals 1/3 x minus 2 squared times x plus 3, I notice one of my zeros is x equals 2. You don't have to set it equal to 2 and solve. You can just see it right there. The other zero I have is x equal to negative 3. The only one, x equal to 2, is in order 2. So that means it's going to touch the x-axis and just bounce right off. So if you want, start drawing a sketch of your function. And locate your zeros. So one is at negative 3, and one is at 2. Okay, the leading coefficient is positive, so that means it's going to end up in this area up here and end up in this area down here, because this is a cubic function. I can tell it's a cubic because I have x being multiplied twice, so x squared times another x, so it's x cubed. Okay, so I know it just bounces off here like that. It's got to be above the x-axis in order to fit, and because the other one is order 1, it's just going to cross right through. Now, some other pieces of information you can figure out is you can also figure out f at 0. So you can substitute 0 in and see what you get. So if I get 1/3 times negative 2 squared times 3. Okay, so that's just going to give me the value of 4. So I now also know my y-intercept is at the value of 4. Now, some other pieces of information. You don't know where the maximums or minimums actually occur unless it's one of the zeros. So you're just piecing the rest of this together as best as you can. Most likely this is actually going to go up a bit and come back down, just because of the shapes I know based on math that I do know. But if you wanted to, you could have made that point at 0, 4 as a maximum. And there we go. That's how you sketch that function. Okay, so let's sketch g of x. I'm going to start out by just drawing a Cartesian plane. Again, I can recognize my zeros as x equals to 2 and x equals to negative 3. X equals 2 in this case turns out to be a order 3. Hey, look at that. The zeros are the exact same spot. Interesting. Well, that's going to give us a different function because this is an x cubed times another x, so x to the 4. So it's going to give me a quartic. This is a quartic and a negative leading coefficient. It's going to end up down here in these areas. So I'll draw those little arrows to begin with. That's again because of the negative leading coefficient. It's going through the value of x equal to 2 with an order of 3, so it's going to kind of like just hover like that, and it's going to go through x equals negative 3, just going straight through. Okay, so again, you can substitute the value 0 in. So you can figure out what the actual, oops, you can actually figure out what, sorry, lost that graph there for a second, hold on. Substitute the value 0 in. Okay, I'm going to grab my calculator here to calculate this. Turns out to be 96. So that means it's going to touch the x-axis at value of light 96. Now again, most likely because of the -3 being a 0 and 2 being a 0, most likely it's going to go up above and come back down like this. But again, you don't have to know that part of it, just being able to identify the zeros and maybe an intercept, that's all you need. And there you go, there's your function g of x. And thus concludes this lesson.